So this video will just be a little review of limits, what we did in Pre-Calculus 12B. We're going to explore limits a little bit further in this course. We're going to look at limits of trig functions and something called L'Hopital's rule. But first, let's just have a quick little review to kind of refresh our limit skills working with limits. So first of all, we're looking at a function here called g at x. All right. G at x is this kind of piecewise function that you see in front of you here. We're asked to evaluate these 6 things, right? I suggest that if you're asked to find a limit, like you are in all 6 of these things, that you get yourself a little straight edge or something where you can place it on the x value. So in the first example, it wants to know the limit as x approaches 2 from the left. Well, first of all, I'm going to put my straight edge where x equals 2, which would be right here. The reason I like to do that is because it divides your page into a left side and a right side. Okay, so what I would do here is I would approach from the left. So that's this portion of the curve. And I'm working my way back towards the next value of 2. When I hit the straight edge, you just got to read the height you arrive at. Okay, it doesn't matter that I arrived at a hole. I arrived at a height of 3. This time I want to find the limit as x approaches 2 from the right. So I don't need to move the straight edge. What happens here is I'm actually working with this side of the curve, the right-hand side, and I'm working my way back towards an x value of 2. And when I hit an x value of 2, I arrive at a height of 1. All right. Now, in order for this to exist, the left-hand limit must equal the right-hand limit. Well, we can see that they don't equal one another. All right, 3 does not equal 1. So what we would say here is the limit as x approaches 2 of g at x does not exist. Okay, now we want to go to where x equals 5. So I'm just going to move my straight edge or your ruler, whatever you're using, to where x equals 5, so 5 units to the right. And again, I'm going to approach from the left, from the right, and then I'm going to see what the limit is. So if I approach from the left, I'm on this piece of the curve, it hops down, and I'm working my way back, and I arrive at a height of 2, right? If I approach from the right, that's this short little piece of the curve here, but I'm working my way back towards the next value of 5, and I also arrive at a height of 2. So when I hit the fence or the straight edge or this green dashed line, okay, I arrive at a height of 2. Since the limit from the left equals the limit from the right, the limit as x approaches 5 of g at x equals 2. Now, when you're asked to find something like this, g at 5 or g at 3 or g at whatever, okay, that's when you can remove this little straight edge. And what you're looking for here is the defined height of the function when x equals 5. So if I go 5 units to the right, I have a closed dot right here, and I have a open dot at height of 2. So the closed dot looks like it's at a height of about 1.2. Well, the rule is when you're looking for the defined height, you pick the closed dot. And I'll call that 1.2. So defined height, little note, is the closed dot. So it's that little dot that's kind of suspended or floating in midair. Now, if I ask for this, g at 2, all right, don't need the straight edge. It's not a limit. I'm looking for the defined height. Well, when I go 2 units to the right, I've got an open dot at 1 and an open dot at 3. Well, there is no closed dot. That means it is undefined. Okay, so that's what I'd say. It's undefined when x equals 2, or g at 2 is undefined. Okay, here's another example for you to try. You can try this on your own, so pause the video, give that a shot. All right, and when you flip the page, or I'm going to flip the page here, these are the solutions you should get. So you can check to see how you made out with that. All right, now we're going to evaluate a couple of limits. Didn't realize there was one still down here, but that's fine. I'll just leave that solution there and we can look at it. All right, so for starters, we have a limit at infinity. All right, limits at infinity, you have to compare the degree of the numerator with the degree of the denominator. So what I'll do first is I'll expand the numerator, 2 minus 3x squared times 2 minus 3x squared. That would give me 4 minus 6x squared minus another 6x squared. All right, so that'll give me minus 12x squared. And then negative 3x squared times negative 3x squared would be positive 9x to the fourth. So remember, 2 minus 3x squared to the power of 2 would mean this. And when you multiply that out, this is what you would get. Here, 2x squared times 3x squared gives me 6x to the fourth. That's minus 10x squared plus 3x squared, so that's minus 7x squared. And positive 1 times negative 5 gives you negative 5. All right. Now, if you remember your rules, okay, quick way of doing this is the degree of the numerator is 4, the degree of the denominator is 4. If they are the same degree, your answer will be the quotient of the leading coefficient. So what's in front of this x to the fourth? 9. In front of this x to the fourth is 6, which would give you 3 over 2. Now, my guess is that when you get to university, your prof will ask you to show the work, okay, on that. And in order to do that, we divide all of the terms in this limit by the highest degree that is present in the denominator. So if I looked at the denominator, the bottom of the fraction, the highest degree would be this x to the fourth. So I'm going to divide everything by x to the fourth. This will simplify, okay? Make sure to keep your limit notation rolling down. So you've got 4 over x to the fourth minus 12 over x squared plus 9. I've got 6 minus 7 over x squared minus 5 over x to the fourth. Okay, so I just simplify. Now keep in mind that as x approaches infinity, this piece and this piece and this piece and this piece would all approach 0. 4 divided by a really large number would be 0. Same thing, 12 divided by a really large number would be 0. These would be approaching 0. Nothing would be happening to the 9 or the 6. So it's at this point I can drop the limit notation and I end up with 9 over 6, which is 3 over 2, okay? Which is the answer we had up here. So remember, know your rules, and you can kind of gauge on what your professor will want next year. Okay, maybe they'll be okay with that. All right, next example. Limit as x approaches 2 of the square root of x minus root 2 over x to the fourth minus 16. First thing I want to do is try direct substitution. Okay, fire a 2 in for x. We get 0 over 0. Remember, that is indeterminate. So that is an indeterminate form. To get rid of the indeterminate form, there's several techniques I could do. We can factor, we can rationalize, we can expand and simplify, expand, or we can use common denominators. All right, that's if you have a complex fraction. All right, in this situation, in order to get rid of the indeterminate form, I am going to multiply both the numerator and the denominator by the conjugate of root x minus 2, which would be root x plus 2. I'm also going to factor the denominator. the x to the fourth minus 16. Now keep in mind, the reason I want to do this is because I want to get a factor from the numerator and the denominator to cancel. All right, I want to get rid of that discontinuity essentially. We're going to talk about discontinuity on the next slide. Okay, so when I multiply something by its conjugate, shortcut is to just go first term times first term, last term times last term. So I've got an x minus 2. All right. Now, down here, I can do the difference of squares. That would be x squared minus 4 times x squared plus 4. And don't forget this, root x plus root 2. All right. Still no factor in the numerator and denominator that's going to cancel. But I do notice that I can do the difference of squares once again in the denominator. So the numerator will still say x minus 2. The denominator, this piece right here, this factor, will become x minus 2 times x plus 2. The x squared plus 4 and the root x plus root 2 follow suit. Now, these guys cancel one another. Leaves a 1 there and a 1 there. And this is where I can go back to direct substitution. So anywhere there's a 2 left, sorry, an x left, I will plug in a 2. All right, here we go. It's going to equal 1 over, you can drop the limit notation. This would be 2 plus 2, that would give me a 4. This would be 2 squared, 4, plus 4 more, that would be 8. And this would be a root 2 plus a root 2, which is 2 root 2. And when I multiply this, I end up with 1 over 32 times 2 gives me 64 root 2. All right, and there we have it, 1 over 64 root 2. You may actually want to rationalize that. It makes zero difference to me, but if you rationalize it, you end up with multiplying the top and bottom by root 2. So 64 root 2 times root 2 would be 64 times 2, or 128. Okay, both answers acceptable with me. Okay, let's look at this guy. Drag him up a little higher. 0, if we fill zeros in for x, you should always try direct substitution first. That's going to give 0 in the numerator. 2 squared 4, negative 2 squared 4, 4 minus 4, 0 in the denominator. It's indeterminate. All right, so I am going to do a common factor in the numerator. All right, x plus 3. And in the denominator, I am going to do the difference of squares. So I'll set up my brackets. Okay, x plus 2 squared would just be x plus 2 if I take the square root of that. If I take the square root of x minus 2 squared, I'd get an x minus 2. All right, I'll put this in brackets because I know that I need a positive and a negative sign between them. Okay, so the negative is going to change some things in here. The positive doesn't really do anything. So I've got x times x plus 3, x plus 2 plus x minus 2. All right, if you remove those brackets, this is what it would say. Group your like terms. You've got 2x. All right, here x plus 2 minus x plus 2. Group your like terms. 2 plus 2 is 4. Okay, the 2's went away here. The x's went away here. So I've distributed the negative. And you may notice that I've got an x that will cancel from the numerator and the denominator. So once that happens, once I get my discontinuity, or I remove my discontinuity, I can go back to direct substitution. So I've got 0 plus 3 gives me 3 in the numerator. 2 times 4 gives me 8 in the denominator. 3/8 is the final answer. As I said, there was another limit down here. Okay, I'll show you the answer to that one. You can have a look at it. Full screen. In case you want to see them all, something you missed. Okay, feel free to pause the video and check it out. All right, one last example. We want to check for a discontinuity. So it says given the piecewise function f of x equals, all right, check f of x for any points of discontinuity. Well, first of all, we have to recognize where there are possible discontinuities. And we can do that by exploring the domain over here. At, okay, there could be one at -1. And there also could be one at 2. How do I know that? That is where the function is changing from 3 minus x to 4. It's changing at -1. And it's changing from 4 to 8 minus x squared at 2. All right? So remember, there's 3 rules for continuity. 1, so let's test x equals -1. First thing I have to do is find f at -1. Okay, so let's look at this function. Where would f of x be defined when x equals -1? All right, well, my choices are this piece or this piece. And the answer would be the second piece right here. F at -1 would be defined on this portion of the curve because it says x is greater than or equal to -1. It can equal -1. So I'm looking at this portion of the curve, and f at -1 would just be 4. All right, this portion of the curve is just a horizontal section. All right, next thing I need to do is find the limit as x approaches -1 from the left of f of x. So for the left-hand limit, we would be looking at this piece of the curve because these are x values that are less than -1. All right, so this side would be approaching from the left. So that would equal 3 minus x. So the limit as x approaches -1 from the left would equal 4. All right, keep going because the left-hand limit does equal the defined height. Let's see if the right-hand limit, all right, so we'll call this 2a and 2b. Next, we need to find the right-hand limit as x approaches -1 from the right. That would be this portion of the curve. All right, so the limit as x approaches -1 from the right would equal 4 as well. I guess I already have that right here. So a limit does exist. The left-hand limit and the right-hand limit are equal to one another, and the limit actually equals the defined height of the function. So part 3 would be to show that the limit as x approaches -1 of f of x equals f at -1. So all 3 of these conditions are met. So we could say the function is continuous at x equals -1. Now we have to check positive 2. So now we'll explore the x value of 2. All right, and before I scroll down, we'll have to try and figure out what portion of the curve f of x would be defined when x equals 2, and that's this piece right here. All right, x equals 2. When x equals 2, y equals 1. So for x equals 2, or at x equals 2, we can see that rule number 1, f at 2 is equal to 1. All right, that's this portion of the curve right here.
Next, we'll check the left-hand limit. So 2, the limit as x approaches 2 from the left of f of x. That's going to equal the limit as x approaches 2. What portion of the curve would be x values that are less than 2 left of 2? Well, that'll be this piece. Okay. And on that portion of the curve, okay, there is really no formula I'd use. It's a horizontal section once again. The height is always 4. So the limit as x approaches 2 from the left of f of x would equal 4. Okay, I can stop right now. Right, I know it is discontinuous. At x equals 2. All right, because the defined height of the function is 1, and the limit, well, the left-hand limit anyways, is 4. Okay, if I checked the right-hand limit, that would be this piece of the curve. All right, 8 minus 2 squared, that would be 8 minus 4, it's 4 as well. So it's discontinuous, so it is defined and a limit exists, all right, but they don't equal one another. So I'll move this out of the way, show you what I mean by that, but you don't even have to go any further. You can stop right here. So the limit as x approaches 2 from the right of f of x would be the limit as x approaches 2 from the right. We're on the portion of the curve 8 minus x squared. That would equal 8 minus 2 squared would equal 4. Okay, so the limit as x approaches 2 of f of x equals 4. It has a limit. It is defined at x equals 2, but they don't equal each other. F at 2 does not equal the limit as x approaches 2 of f of x. So therefore, it's discontinuous at x equals 2, and it's actually called a point discontinuity. Or a removable. All right. If you were asked to sketch that curve, this guy right here, this is what it would look like. And you can see that when I draw the curve, it'll prove it's discontinuous at x equals 2. I've done that on this page here. So there's the first portion of the curve, that linear section, another linear section, and then this quadratic section, and then this kind of point suspended in midair. Well, the rule is this. If you have to lift your pencil when drawing this curve, which I would right here, I'd have to lift my pencil to draw that dot and then come back up and make this piece. If you have to lift your pencil, the function is discontinuous anywhere you lift your pencil. So in this case, it would be discontinuous at x equals 2. Okay, so that's a little refresher with limits. The next couple of videos, we'll get into some stuff we did not see in pre-calculus 12b.